The cool thing about knowing the process transfer function is that now you can simulate other kinds of inputs and see how your output will respond to it. Because as you'll recall, what is the whole point of a transfer function? It is to map an input to an output. It tells us how our output, like temperature, will respond to an input such as an increase in heater duty. And so what I'm going to do in this video is go over how, if we know GP, we can determine what y of t is, the output response in the time domain to a new input. And this is very useful for process engineers because we're not going to know what kind of inputs are out there, but we can always simulate them with our transfer functions. And so the first thing we're going to do is we obtained previously this plot. Think of it like temperature versus time. When we increased the reboiler duty, we obtained a lag. We also determined the gain and the time constant in this form here. And what we're going to do now is say, let's say there's an impulse input that occurs. And we want to know how will our output respond. Sorry. And so the first thing to do is recognize what is an impulse input. Impulse inputs in the time domain, which I denote u of t, are equivalent to Dirac deltas. And in the frequency domain, when we take the Laplace transform of u of t, we get 1. It's a very nice, easy function to work with. And so if we go back to our definition of what the process transfer function tells us, y over u is equal to 2 over 3s plus 1 times an exponential of minus 2s. And because we know that u is equal to 1, we can multiply both sides by 1 and cancel everything out. And this is y of s. And so now we want to work backwards from the frequency domain into the time domain to see what this is like in time. And so to do that, we're going to be taking the inverse Laplace transform of y of s, and we know that this is equal to y of t, which is equal to the inverse Laplace transform of 2 over 3s plus 1 times the exponent minus 2s. What we do now to not have to do any Pade approximations of this time delay term is we will recognize that this is essentially equal to f of s, and we'll let 2 be equal to t naught, and we will look at this definition here, which tells us that we can approximate this in the time domain as simply a shift by t naught. And so what we're essentially doing now is I'll take the inverse Laplace transform of simply 2 over 3s plus 1, and then we'll throw in this t naught term later. And to do that, to get it into this generic form here, I'm going to divide every term by 3, and we can also pull out the 2 or whatever constant is up top. And so when we do that, we divide every term by 3. This is equal to the inverse Laplace transform of 1 over s plus 1/3. And if we evaluate what 1 over s plus 1/3 is, we'll realize how b is equal to 1/3. And so now when we plug everything in, we will find that y of t, due to an impulse input, is equal to 2/3 times the exponential of minus 1/3, which is b, and then times t, and then we're going to shift it by t naught here, so t minus 2 because of this delay in our output that we observed previously, and this is equal to y of t. And so if we wanted to know how the temperature of our system will respond to an impulse. We can think of it maybe as like a power surge or something. What we would find is that y of t over time will be 0 until 2 seconds, because at 2, e becomes 0. You plug in 0 into your exponential, it will jump up to 2/3, and then it will decay exponentially back down to its previous steady state value. And this is the kind of response that we would expect to see from our system based on this graph. So the nice thing about this is we're able to model and predict how our output will respond to other types of inputs and other magnitudes of inputs once we know these process transfer functions by following this procedure. So I hope you guys find it useful. Let me know if you have any questions, and thanks for watching.